We are going to start chapter 6 now, which is additional topics in trigonometry. And where we will begin with this is what's called solving what are called oblique triangles. Oblique triangles are simply triangles that do not have a right angle in them. So, the two methods we're going to use are what's called the law of sines, which we're going to cover in section 6.1, and also the law of cosines. So in this section, you should be able to apply the law of sines to solve oblique triangles and also identify when the law of sines can be used. Okay, so with that, remember, whenever you see the word solve or solving a triangle, it means find the missing parts. Whatever you're given, find whatever's missing. That's what it means to solve. When you're asked to solve, you must know the length of at least one side and any other two pieces of information in the triangle. So these are the four cases. You can be given any side and two angles. So angle, angle, side, meaning the side is not between the two angles. Or angle, side, angle. In this case, the side would be between the two angles. You can be given two sides and an angle opposite one of them, which is the side-side angle. Three sides or two sides and their included angle. Now these first two is when the law of sines can be used. Okay? Law of sine can be used in either of these three cases. Angle, angle, side, angle, or side, side, angle. The other two, you need the law of cosines to do, and that will be done in section 6.2. So let's get started. The first thing I'm going to do is actually derive what the law of sines is. So you can see an oblique triangle here. That's not a right angle. It's an obtuse angle, it looks like. So I've got triangle ABC here with sides little a, little b, and little c. First thing I'm going to do is drop an altitude. Altitude, again, is a segment from a vertex perpendicular to the opposite side. So again, what I've done, I've drawn this in here so I have a right angle formed by that altitude with the opposite side. Now if you look at this, I have two right triangles that are formed here. I've got the one with angle A over here going to the bottom part of the altitude there up to point C, and I've got the one on the right. Okay, on the left, what I'm going to do is look at angle A, look at the altitude that I just drew down, I'm going to call that H, and also this side over here. And I'm going to use the trig ratios that we do already know to write a trig ratio that involve those three parts. Well, what would that trig ratio be? I've got angle A, I've got the hypotenuse or the opposite side H, the height, and the hypotenuse of that smaller left triangle there. So opposite over hypotenuse is the sine. So I'm going to say the sine of angle A is equal to H over little b. Okay, now what I'm going to do with that equation is isolate the H. So I'm going to solve for the H. I need to multiply both sides by b to get rid of that denominator. And I end up with H is equal to little b, side b, times the sine of angle A. I'm going to do the same thing with this triangle that's formed on the right-hand side of this using angle B, the height again, and little a. So again, I use the same ratio. It's the sine ratio because that's my opposite leg in that triangle of angle B, and there's my hypotenuse. So I'm going to say in that triangle, the sine of angle B is going to equal the opposite leg, which is the H, over the hypotenuse, which is A. Like I did over here, I want to isolate the H, so I'm going to multiply both sides of this equation by A, and those end up canceling. I end up with H is equal to side A times the sine of angle B. Okay, this H and that H in those two equations are naming the same thing. They're both equal. So what that means is then this, the B times the sine of A, must also equal A times the sine of B. So what I'm basically going to do is take this, B times the sine of A, and replace it in this equation where the H is at. So I end up with B times the sine of angle A is equal to A times the sine of B. One more step and I'm done. I'm going to divide both sides of this equation by the two segment lengths, A and B, and then reduce my two fractions. So on the left-hand side, my B's are going to end up canceling, and on the right-hand side, my A's are going to end up canceling. And I'm left with the sine of angle A over little a is equal to the sine of angle B over little b. And that right there is a proportion that is the law of sines. If you look at this, what I have is the sine of an angle, which is angle A right here, over the side opposite. Opposite angle A would be little a, is equal to the sine of angle B, which is right here, over the side opposite, which is over there. If you know any three of those four pieces of information, you can substitute those in and solve the equation for the missing part. I could also extend this formula to include angle C and little c, and I'm doing this on the next slide. Here is actually the law of sines, and there is what I would have come up with if I would have included angle C and little c as well. I want you to also remember that with proportions, you can take the reciprocals of the fractions, and those fractions would also still be equal. So you can put the segments on top or the angles on top. It doesn't matter, they're interchangeable. What I typically do is, if I'm looking for a side, let's say I'm looking for side A, and I know angle A, and I know side C, I know side C, and I know angle C, I would throw out this one, use these two fractions here, and use this formula because the A is in the numerator. It always makes it easier when you're trying to solve because you're not having to turn around and multiply and then divide. Like if I had these two fractions over here, I would have to multiply both sides by A and then divide to get rid of the sine of C. So it just makes it easier. Alright, let's see one of these done. Alright, here's an example. Solve the following triangle. One key thing here is it's not drawn to scale. Well, first off, let's look to see if we can actually use the law of sines. I can see in this triangle I'm given angle A is 35 degrees. I'm given angle B is 40 degrees. And I'm given side C, which is 10. Well, let's look at what I've got. I've got two angles and the side that's between them. So that's my angle, side, angle case, which was one of the ones I said you could use the law of sines are. If you go back, right here, law of sines, angle, side angle. So we're good to go ahead and use the law of sines on this. So, solving. Find all the missing parts. Well, I don't even need to use the law of sines to find my first missing part, which is angle C. The way I'm going to find angle C, if you remember, the sum of the three angles of a triangle must add up to 180. So all I'm going to do is take 180 and subtract the 40 degrees and subtract the 35 degrees from that. And I believe if my arithmetic or subtraction is correct, it ends up being 105 degrees. So there's the measure of angle C, 105. If I can get that degree measured right on there. That almost looks like 1050. That should be 105 degrees. Okay, so let's continue to try to solve this triangle. Let's focus in on angle A, or side A. Remember, the law of sines is the sine of an angle over the side opposite. So if I'm looking at side A here, the angle opposite would be the 35 degrees. Turning your attention to the one side you do know, the angle opposite that is 105 degrees. Now I'm going to use the proportion that puts the segments in the numerator because that's what I'm trying to solve for. And when I set this up, I'm going to say that A over the sine of the angle opposite, which is 35 degrees, will equal 10, which is segment C, over the sine of the angle opposite that, which is 105 degrees. Now to solve this proportion, I'm going to multiply both sides by the sine of 35 degrees, And when I do that, A ends up being equal to, let's see, 5.9. And I should say that's approximately equal to, so I'll put that little squiggly equal sign in there because it should be approximately equal to that, not exactly equal to that. Now, one last thing to find, segment B. So that ratio or proportion I'm going to set up is little b, side B, over the sine of the angle opposite, which is 40 degrees. So B over the sine of 40 is equal to 10 over the sine of the angle opposite that, which is 105 again. Just like I did in the other one, I'm going to multiply both sides by the sine of 40. And when I get done multiplying that all the way out, B ends up being approximately equal to 6.7. Okay, and a quick check. Remember, in a triangle, the largest angle is going to be opposite the largest side, which is the case here. The smallest angle in this case is 35, and smallest segment is little a, which is 5.9, which does jive with what you should have learned in geometry. Let's look at another example. One more final example here. This time I'm not going to give you the picture, I'm just going to give you some information. I've got angle A is 105 degrees, angle B is 25 degrees, and side C is 10. Let me go ahead and draw a picture. I'm going to start by just drawing angle A first because I know it's an obtuse angle. So I'm going to make it a little more 90. So I'm going to label that as A. Put my 105 in there. This will be a little more to scale than the other one was. I must be hitting the button there. 105. I'm going to draw just a segment over here to connect. The rest of this won't be drawn to scale, so I'll put B there, C there. Little c is going to be opposite angle C. That's this segment over here, which is 10. Angle B then is this angle right here, which is 25 degrees. And again, it looks like I've given you the case of angle, side, angle. I've got two angles in the included side. So, to find angle C is going to be equal to 180 minus my other two angles. My other two angles add up to 130. So that means angle C is going to end up being equal to 50 degrees. So there's the first part of my solution. I've got angle C is 50 degrees. Okay, let me find little a next. I'm going to label little a. I always try to find the longest segment first. So here's little a. I'm going to set this up as the sine. Actually, I'm going to set it up as little a over the sine of 105. And that's equal to 10 over the sine of 50. Multiply both sides by the sine of 105. A ends up being equal to, and you end up with an answer of 22.9. Likewise, if you turn around and do the same thing to find little c, and you can go ahead and try that on your own, little c should end up being 5.5. Okay, oh, I should have wrote that here. Sine, what I did again was multiply by the sine of 105 degrees there on both sides to get that a by itself.